Hey everyone, it's July 21st. Oh, another day working late, and then came home, had to eat, and finally getting ready to do today's challenge. So this is the challenge, partition list, whatever it is. I'm not sure if I have time for this, but even if I have, I'm not sure if I think I'm gonna go for the hint. I slept on it and didn't have an idea, so let's just go finish this. Oh, we're on the topic of linked lists. Ahead, and value x. Partition is such that all nodes less than x come before nodes greater than or equal to x. So basically, a quicksort, right? A pivot. Count before nodes greater than or equal to. Yeah, it's like a pivot. So if it's a 3, then these come. Hold on. All nodes less than x come before nodes greater or equal to x. You should preserve the original relative order of the nodes in each of the two partitions. So for here, node x is 3, so all the nodes such that all the nodes smaller or equal to 3 come to the front, and a larger equal to come to the back. So basically, we do not change the order, we just get the smaller ones in the front and the bigger ones at the end. Okay? So 3. We can go boom 4. So this one need to be moved to the back. So what we can do is, we can create a separate, and then once we're here, we just push it there. Once you're here, we push it there, and this one we don't push. This one we push it there. Yeah. So two linked lists, and then we put them together. And memory-wise, we're not really using anything more. Oh, jeez, what was that? Oh, I have a foo. Yeah, this is from yesterday. Two. Alright, I'm not gonna test this. So, what do we have? We have a dummy. We're gonna call it a list node. Okay, and then we say the bigger. Okay, we say the bigger one. Bigger equals dummy. So we're gonna have say node equals head. Right, while node, if node.val is larger or equal to x, then we're gonna cut it out. Oh, we have to have a dummy. Let's say dummy small. This node next equals head, and then dummy big. Right, and then have a bigger is dummy big. Okay, so node is, we need to have a pre-current equals dummy small, and current is going to be head. Okay, so while current is larger than, then we need to cut it out. How do we cut it out? We can just say pre.next equals current.next, right? Pre.next equals current.next, so we cut it out, and we put current, we say bigger right, dot next equals current. Right, bigger dot next equals current. And pre doesn't change because I cut it out. Pre doesn't change. So current equals pre dot next, and bigger equals bigger dot next. Right? Bigger equals this, so bigger need to move on to the next one. Okay, so now we go on. If it's small, if it's still larger equal to, then pre didn't change, so pre dot next equals current dot next, so we point in there, and bigger dot next, bigger or move forward dot next equal to current, and current equals pre dot next, current pointed to 2, and then bigger equal to bigger, move on. And keep going. If it's smaller, then nothing changed. And if it's smaller, both need to move. Current equals current dot next, pre equals pre dot next. Okay, so move on. Okay, so eventually, once we're done, current will be none. So pre is the last one. So we say pre dot next shall equal to dummy big dot next, right? Dummy big dot next, and I'm going to return dummy small dot next. Okay. Oh, we found cycle. What the hell? All right, it's not right. Okay, let's see. So dummy small pointing to head. Dummy big. I probably forgot to clean out some of the links. Dummy big is just a list node, and bigger is on the dummy, right? And pre is small, current is head. To understand, current, then pre dot next equals current dot next. So we'll link this one, right? And bigger currently is the dummy. So bigger dot next equals to the current, which is right. And maybe what we need to do is cut this tie. So we have a tie here. So bigger dot next is current. And current dot next is still, so bigger to here is still pointing here, right? So what we need to do is bigger dot next equals current. And current dot next equals none. Okay, let's set current dot next equals none. So just shut up, shut up this link. No longer link to anything. And then current equals pre dot next. Yes, let's try this one. Yep, looks like this one is good, but we're gonna try another one. Oh, maybe I should try a smaller one. How about this? Okay, seems to be right. Huh, I used to do in Java. Okay, let's see. Yeah, linked list is always a little bit easier for me. Linked list and trees cut out the bigger nodes into its own list, and then merge the two, merge the smaller and bigger lists together. 168 test cases back then. Oh, slower than before. Are we creating a new node? Ah. Oh yeah, this is creating new nodes. And then we clear out this. It's alright. Doesn't really matter. Alright, so we have time. Alright. Let's take a look. Real topic. Dynamic programming. Monotonic stack. I was thinking about monotonic stack. I don't know how to use monotonic stack. And prefix sum. Yeah, I'm pretty sure we have to use prefix sum. This overall, still have no idea how this can work. A piece of paper. Oh, jeez. I just tore off the paper. Okay. I got the paper. Alright, so with the mindset of prefix sum and a monotonic stack, that was what I was thinking, right? Because I was thinking, if you increase, every time you decrease, and you can get rid of some. You can get rid of all of them until the previous smaller one. That's true. That's what the small one comes in can do. So everything that, and actually the one that's smaller equal to. So everything that's smaller than you cannot handle. Those are just way too much. So is it possible that as we go back, right, as we looking back, can we use prefix sum to quickly calculate what additional things we need to do? Now the thing is, not even thinking about the monotonic stack. I just have, let's say I have 1, okay? Now I have 3. 3 is bigger than 1, right? So how much I shall add? 1 is 1. 3, I know I need to add 3 times 3 is by itself. Then, because 3 is bigger than 1, so I know 3, 1 need to go with 1, so that's 1 times 4, right? And if it's bigger, right, we say it's a monotonic stack. So every time you add something, if it's not smaller, right, if it's bigger, then it must be the biggest one. So all the subarray ending at it right? So we have this over to the front. They have to multiply by those things. But the thing is, how are we calculating this without having to go through the whole thing? It would be like you have to go through the entire thing, right? Or maybe you say we can save it. Save it. How do you save this? Well, we can see how many subarrays are using this as the smallest value. If we're in increasing, then if we pick any value, then all the subarrays starting from this going down are using this. So we are saying this plus this plus this, they all need to multiply by this. So all I need to know is what's the sum. So let's become, if we say this is A1, A2, A3, A4, if A1 is the smallest, so A1 plus A2, A1 plus A2 plus A3, and A1 plus A2 plus A3 plus A4. All of these rely on A1, so all of these into times A1. And for A2 is going to be A2, A2 plus A3, A2 plus A3 plus A4. They need to time A2, and A3 is going to be A3, right? And then A3 plus A4, and A4 is just A4 by itself, right? So that's how it kind of works. And if you look at this, if you look at this, if we have this thing, A1, right? If we have A1, so basically it's 4 times A1 plus 3 times A2 plus 2 times A3 plus A4. That's the sum of the entire thing, right? The sum of the entire thing starting from A1, if we have this linked stuff, right? That's like the entire thing. So if we have this entire thing, A1 times this whole thing, right? If we have this, A1 would time this whole thing. And then we say this is S. Then A2 actually time S, if you think about it, is A2. So minus 4 times A1. And A3 is times S minus, and if let's call it S1, right? And this we call it S2. Then A3 is S2 minus 3 times A2. And A4 is S3 minus 2 times A3. So this means if we find, but then we need to know how long this stretch is, right? So like we keep we keep counting the stretch. Once we find the stretch, now now we can run the stretch again, and we have the total number. So we say it's gonna be, and then we can do the sum. So we run. So we find a stretch. Once we find a stretch, we'll run this thing again to compute the total thing. And after we compute the total thing, and from the first we compute this, we have this one, and the second, third, and fourth. So we can compute the sum, the total strength, in a increasing fashion, right? In an increasing fashion in O2n. Okay, O2n, we can do that. That's like solving half the problem. Now the other half of the problem is when we encounter something smaller. And when we encounter something smaller, what we're gonna do is we're gonna skip, right? We're gonna pop. And how do we pop? Well, so now what we have is a stretch. So what I want to do is we accumulate, right, monotonic increasing, and we don't calculate it. And then once we find a smaller one, then we'll pop some stuff. And as we pop, whatever those popped, they need to be computed, right? They need to be computed to, attribute to whatever this one is. And but we don't compute anything that's not popped. So eventually, at the end, this entire thing, yeah, this might, okay, hold on. So now let's say we have A1, A2, A3, A4. Now A5 comes in, but A5 is smaller. Let's say A5 is smaller than A2, 3, 4. Okay, 2, 3, 4, A5 is smaller than that, but A5 is larger than A1. So ideally, I will pop A4, A3, A2, right? I'll pop them. But what about the things that they represent, right? So what we see is when we pop them, we have tremendous value that we need to add, because if you pop them, you're losing, right? You're losing stuff. So if A5 is smaller, how do we incorporate this? Well, A5 is smaller than A4, which means well, A5 is larger than A1, so you can say whichever is smaller than A5, the biggest one that's smaller than A5. That one doesn't change. That one can still reach A5, right? That one can still reach A5. But these things, when they go to A5, they have to multiply by A5 instead of multiply by themselves. So it's still this plus this plus this plus A5, but we need to multiply by A5. we can pop this out, right? But they can be represented. Their value can be represented. Right? Their value can be represented. So every time when we convert when we pop A2, A3, I can compute whatever they contribute to, right? And then once we do that, we can have basically just we can have A2 and A2 plus A3, A2 plus A3 plus A4. This whole thing can become a thing that will attach to A1 because A1 has to go through. So it's like, oh no, but A1 to A2, you're losing that one as well. Yeah, I have to look back, right? We cannot look forward. Because the idea is to pop it. Let me redo this. I'll look back. So A1 is just A1. Right? A2 is going to be A1 plus A2. No. A2 look back is A1. Yeah, that's the thing. If A2 looks back, it can be A1. It's not based on A2. I want them to be based on A2. So they have to look forward. But boom, we hit something. Right? Which means because in the future, it depends on A5. Yeah, let me just play around a little bit more. You know what? Maybe I should just compute the upward trend. Compute that. And now I have something smaller. Then we don't have to worry about anything related to that because now A5 is smaller, let's say smaller than A4, A3, A2. So everything starts from this will no longer bother them. It will all be on A5 until we find something even smaller. Okay, so A5 is the new thing. It's just, it will handle A4 to A5, A3 to A5, A2 to A5. Let's say if I have this, okay, and then for A5, still no idea. It's all right. Let's see hint number 1. Consider the contribution of each wizard to the answer. Each wizard to the answer. So the total contribution. Okay, the total contribution, if we think about one wizard. If the wizard has power 1, total contribution is just, it's by, so all the subarray that it's involved in, and involves in lots of subarrays. How many subarrays are there? And if it's 1, then they will all multiply by 1, right? Like if you are here, then on just this, these are all the only things that are involving you. Then we can actually compute the total strength, because it's always a sum, right? So it's just by itself. But if it's this one, then we have everything ending in 1, everything starts in 1, right? And everything crossing 1. That is a lot of things. Okay, what's next? Total contribution answer for all subarrays that end at each index. Okay, we're talking about AMP. The total contribution to the answer for all subarrays that end at each. So, can you calculate the total contributions for all subarrays that end at each? So if we find something and the total that end at this, yes, we actually know. And if it's 1, it's easy. It's just this plus this plus this, and that's done. It's easy for 1, right? Because we know it multiplied by 1. But if it's 3, like ending at 3, so ending at anything, okay? If we have an A, we're ending at A. We know by itself is A times A, and something in front, right? If it's smaller, we use this. If it's bigger, we use this. Like ON. But that's not efficient, right? That's not efficient. We want an efficient way to compute this. Okay, last hint. So it's like dp. Total contribution of all subarrays ending at index I as this dpi. Can you solve dpi in terms of solving dpm? Yeah, that is a dp idea. It's kind of pointing us to a direction, so I'm going to try it then. So what we're saying is, if at each one, what we want to solve is the total contribution, just the total score, right? Total strength ending at this, and then we just add them together, will become the result. So the total ending at this, right? Let's, I don't know, write it out. If we have here, so the total ending at this one is 1 plus 1 plus 1 times 3 plus 1 plus 1 times 1 plus 3 plus 1. That's the total contribution here. Now that 3 is 3 plus 3 plus 1 times 3 plus 1. And a 1 is just 1 plus 1. So that's the 2 in front. How does this help? Well, definitely not itself, right? But we have a connection and a connection. If we think about it, we have a connection. Hold on. Okay. I want to find out this. To find out this, we need to know this, this, and this, right? That's what I want to know. The sum of them. And the sum of this, we can know. The sum of this, yeah, we can know the sum. The sum is 0,1. And of course, the sum of this, right? And what we also know is, let's say, we want to know the sum of A3 plus A4, A2 plus A3 plus A4, A1 plus A2 plus A3 plus A4, right? And what we notice is for A3, we have A3 plus A2, A3 plus A2 plus A1, A3 plus A2 plus A1, A3 plus A2. So it's kind of in there already, right? So we can have this and then multiplied by how many we need to go, right? So if A3 is something I have to get, it's actually this A3, right? A3 is by itself and A2 plus A3. So just this whole thing plus 3 times A4. If A4 is the smallest, right? If A4 is the smallest. But what if it's not the smallest? Right? If A4 is not the smallest, then we'll have something that's smaller than A4 and something that's bigger than A4. If those are something bigger than A4, let's say A3, now we know A4 to A3, A4, A3, A2 will use A4, but A4, A3, A2, A1 will use A1, right? So we have these smaller ones. Can we have an efficient way to compute A3 and let's say A3 plus A2, right? Because that's all I need. I want, so for everyone, So let's say we have a total sum of the increasing stretch, okay? Total sum of an increasing stretch. For an increasing stretch, for an increasing stretch, anything will be that minus that. So I can say to A2, okay, so that's we can have this. So this belongs to A4. So I can calculate that. So basically this plus 3 times A4. These all belong to A4, so we can add that. Okay. And how about A1? Now, A1 does not contribute, is not A, so we have to add A1 all the way to A4, contributed by A1. So we can do that. And we can compute a new thing, which is to A4. Is whatever we have previously to A3, and then we'll add A1 towards A4, right? We add A1 towards, so we have a new kind of S here. Now we can pop these, because these are bigger, right? Because we have two arrays. One array we use to handle these sum. The other array is used as a monotonic stack. So if something bigger comes in, right, something bigger comes in, then its contribution, how do we calculate its contribution? It's whatever is inside the monotonic array. Hold on. If something bigger comes in, don't calculate at the moment. Okay? Don't calculate at the moment. And when something smaller comes in, then we calculate. And how do we calculate? Well, we have a sum amplitude here, so we just need to get a sum for this. We add that. So that's everything belong to A1, so I calculate that. And A2 to this is not dependent on A2, it's actually on A4. So 2, 3, man, it's just so complicated. Okay, these all belong to A4, right? Now I have A4, A3, A4, A2, A3, A4. I have this. This can be computed by whatever the sum minus 4 times A1. That's we can get. So all of this, right? All of this and plus, well, I'll have to do A5. So just 3 times A5. All of this belong to A4. So I can times A4, then we call it. And we go to A1. Right, we go to A1. And A1 will just do, I'll say do the same thing. What do you mean do the same thing? Now I'll do A1 to this. So from A1 to A5. Now it starts to make a little bit more sense. Are you saying we need 2 prefix sum? Like seriously, 2 prefix sum. One is the regular prefix sum, and the other is a more convoluted prefix sum. So if any time a bigger value comes in, and we make sure that the stack that we are on is a monotonic stack, monotonic increasing. So if a big value comes in, I go through everything in this list. Really? You go through everything in this list? I'm not sure. You should not be going through everything in this list, right? Because that's, unless we go through that only once. We only need to go through this once if it's monotonic, right? Because if we have computed everything as we're going along, because if thing comes in is bigger, right, then we go to the things in front, and we can compute the value, the sum of the value in between these two, right? And those will all depend on the smaller one. So the big one, we go to the big one. And in between, we have a value. Then all these values because it's from this to this, this to this. Hold on. These are bigger values, right? Bigger than that. But how do I know they are also bigger than the current one? We know they will not be because it's monotonic, so if they're smaller, they'll pop it out. So they're all bigger than A4, right? So they'll all be bigger. And then A5 comes in. And A5 is bigger, but now if they're bigger, they will stay, right? If they're smaller, they will pop it out, which means everything, like A5 is going to be the next biggest thing to A4. Yeah, that's the rule of monotonic array. So there should be nothing in between A4 and A5, because if it's a bigger thing, the bigger ones will be there. If it's a smaller thing, the small thing will pop A4. So if A5 can be placed right after A4, A5 must be strictly and uniquely bigger than A4 at this time. And when that happens, there's nothing in between. And we just add, right, a monotonic, non-monotonic, the prefix sum, we just add that, okay? And the prefix sum of that, we add that, okay? So we have two levels of prefix sum. Okay, so A6, we just keep adding, keep adding. Now, once a smaller thing come in, okay? Because if no smaller thing come in, we just basically keep doing this until the end, and we have a way to compute their sum very easily. Okay, so now we say we have a smaller come in. So if I is bigger, so we don't consider. Then say A6 comes in, and A6 is smaller than A5. Then I need to pop, right? So when I pop A5. How do we handle? Well, if we pop A5, anything's not on the stack need to be computed. So if I pop A5, right? So which means, well, honestly, I don't think we should wait. I think we are computing everything on the way. But if we compute everything along the way, that looks O(n) squared to me again. So A6 is smaller than A5. Okay, so ending in A6, A5, A6, A4, A5, A6, and everything. Let's say A6 is smaller than A5 but bigger than A4. So only A5 will contribute to A6, right? So yeah, we have this much. Now we just need to find out the sum. We can do that. Yeah, we can binary search to find who is smaller than A6, and then we have this range. And we just need to find the sum of this range. which we can because we have accumulated. So it just becomes this thing, right? Minus, because it's going to be this plus this, this plus this plus this plus this plus this, right? And what we want is this, this. So one, two, three, four. No, 2, 3, 4. Wait, what are we recording again? You've got to be kidding me. What are we recording? We're recording 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 1, 2, and 1. That's what we're recording. Right, if we add something, we just add this one up. So now I want to find, let's say, 3, 4, 5. So that's 3, 4, 5. 4, 5. Yeah, how does that work? Alright, I don't know. I don't want to keep thinking today. I think I'll try a little bit afterwards, but that's it. No point of keep pushing. The brain power is dropping. Yeah, reading the hints is still not helping actually. Can you solve I in terms of M for some M's? That's dynamic programming. But I couldn't figure it out. Like, well, how? Exactly how? I need some intuition. Alright, I'll see you guys tomorrow. Adios.